So I want to welcome everybody to the R&D Showcase. I'm Mike Matheson, Managing Director of Cognite.ca, and we'll be moderating today's session. The series is jointly presented by Cognite.ca and the Canadian Construction Association. The R&D Showcases are part of a broader initiative Cognite.ca and the CCA have undertaken to help the construction industry more fully leverage Canada's $14 billion academic research enterprise. Another major element of is the construction R&D portal, which can be found on the CCA website. Using the R&D portal, you can see construction industry relevant research and search for researchers, research, facilities, and IP that can help you address your company's next innovation challenge. I'll be posting a link to that in the chat and would encourage you to check it out when you have a few minutes. Our format today will be a presentation followed by a Q&A session. If you have questions for our presenter, please click on the Q&A at the bottom of the Zoom window and enter them in the box. I'll read them out during the question and answer portion of the program. For today's R&D Showcase, I'm delighted to welcome Dr. Brady Peters. Dr. Peters is a Canadian designer and associate professor at the University of Toronto who successfully bridges technology and design. He has significant experience in the use and development of design technology in integrative construction and digital fabrication. He will be presenting on robots for architectural design and construction. With that, I'll turn to Dr. Peters.
Hello, everybody. Welcome to this talk. Hopefully everyone can see this. So this is the title of the talk. I'm Dr. Brady Peters. As mentioned, I teach at University of Toronto. I'm also director of an organization called Smart Geometry, which is a not-for-profit organization that promotes design technology for architecture and engineering. Okay, there we go. So this is where I work normally in non-pandemic times. This is the John H. Daniels Faculty of Architecture, Landscape, and Design. We moved into this building actually relatively recently in 2017. The building was originally built 1875 as the home of Knox College. And you can see like the original building in front. In the back is the new addition. And in that new addition, I also have my lab. So this is the robotic prototyping lab where I do some of my research. My research itself, while it encompasses digital fabrication and robotics and construction, right now is really primarily at the intersection of sound and architecture. And we'll see some more evidence of that with some of the projects that I'm going to show. I did my PhD research in Copenhagen, actually at the Royal Danish Academy of Fine Arts, so an arts institute, but I worked at the Center for Information Technology and Architecture, sort of a highly digital and technical group. Prior to that, I was an associate partner with the research and development group of major international architecture practice, Foster & Partners. While at Foster & Partners, I had the good fortune in the sense of not only working with some amazingly talented people, but also working on projects that actually got built. So this is the Kogod Courtyard in Washington, DC, Lime Street Office Tower in London, and the Thomas Deacon Academy in Peterborough in the UK. So the topic of my talk today, though, is about robots. And you've probably come here to hear about robots. So what about robots? It is an oft-quoted explanation and or excuse for the adoption of robotics is that they will do tasks that are dull, dirty, and dangerous. And this certainly presents some noble seeming reasoning. Robots can replace human workers in jobs that could be harmful to human health, thereby moving human jobs to safer, cleaner, and more interesting work. Robots can do tasks that humans cannot do or cannot do easily. For instance, picking up these large planes of float glass. Robots have been classified as what Clayton Christensen calls, can everyone still hear me? I hope. Clayton Christensen calls a disruptive technology, where they've taken established markets and created new markets and value networks that have displaced the original. And this has certainly impacted many different industries, in particular, the repetitive tasks involved with assembly-like work, in like this automotive assembly line shown here. Worldwide, the cost of robots is going down and the number of robots is increasing. With $26.9 billion in global shipments in 2015, this is expected to increase to $67.9 billion in 2025. So the benefits of robots are many. They can do repetitive tasks, they don't get tired, they can work 24 hours a day, they're strong, they're fast, they're precise, they're not concerned with danger, they create new markets and value networks, and they're inexpensive, relatively, and widely available. So, what about the building industry? Where are the robots? It is certainly not for a lack of dull, dirty, and dangerous jobs. Construction has lagged behind other sectors in the adoption of robotic technology. In 2016, McKinsey Global Institute studied the use of digital technology in a variety of industry sectors. And unfortunately, construction did not rank very highly. In fact, the amount of digitization in construction rates right above agriculture and hunting, right at the bottom there. Additionally, we can see that labor productivity in construction has not kept pace with the general productivity increases when compared to the labor market as a whole. So we can see that there's room for improvement here. So robots certainly mean the adoption of more digital practices, and this could therefore also mean potentially an increase in productivity. But what about architecture? While related to construction and the production of buildings, architecture is fundamentally concerned with design. And so what do robots have to do with architecture? The definition of what it means to be an architect is linked to our design tools. As Jonathan Hill has pointed out, it was the invention of drawing that enabled the creation of the architect. The architect is defined by the ability to draw, and the drawing to conceive of and communicate the plans for a building at a remove, both spatially and temporarily, from the construction site. And this has been the way for 1,000 years or more. And so I would argue that it is no small matter that the design tools of the architect have changed. And it also makes sense of the reluctance of the architect to adopt entirely new tools, as their whole definition of their discipline is based on this, right? Ivan Sutherland introduced the world to the first CAD system in 1963, Sketchpad. This system could draw, it had parametric capabilities, it could do simulations and calculate structural performance, it could link geometric designs to numeric databases. Ivan Sutherland recognized that the computer offers considerable potentials that are different and greater than the drafting board. Using computation was not just another way to draw, but a new way of thinking. AutoCAD version 1 was released in 1981, and by 1986, AutoCAD had become the world's best-selling CAD software. However, the potentials that Ivan Sutherland had identified had not been realized, as AutoCAD was essentially just a two-dimensional drafting board. Robert Aish writes that in retrospect, 2D drafting is really a travesty of Sutherland's original intentions. And the spectacular flaw of 2D drafting is that it fails to harness the potentials of the computer as a creative design tool. So 2001, I finished my master's in architecture degree and moved to London, England from Canada to find work and begin my career as an architect. I ended up getting a job at an engineering firm at Bureau Happold, one of the world's leading structural engineering firms, working for the Structures Group in London. And here I had the chance to work as a physical model maker, building a whole range of different types of physical models and doing a whole range of different types of drawings as well, in service of both the making of those models, but also communicating engineering concepts and performance concepts to the clients, which in this case were architects. In the course of doing this, I also began to use digital technology more and more. At first to build better physical models, but eventually this just overtook what I did, and all the models that I built eventually became done in the computer. So this was like one project that I worked on. This is a house, mansion, villa for a wealthy client. You can see on the left of the screen, this is the digital model that we got from the architect. And as engineers, we were tasked with the creation of a comprehensive structural system from this three-dimensional model. And so what I did was basically take this like radial section through it, bring it down to the ground, and create this sort of these structural sections around this sort of more amorphous form to create this physical model. So this move from the digital to the physical. However, like as the design developed and as iterations happened, it became very hard to keep up with this. So I figured like there had to be a better way, right? That would automatically update our design intentions to describe these designs in terms of relationships rather than having to remodel this geometry over and over again. And so I guess it was around 2003, I attended the first Smart Geometry conference in Cambridge and had the opportunity to see Hugh Whitehead speak. And if you recall, like the first slide I showed with this image of the London skyline, the Swiss Re office tower, locally known as the Gherkin, features prominently. And this building was going up at the time I was living there and working at Bear Happold. And so this building obviously was very important to my experience of London. And seeing Hugh present on this project was like important enough, but then for him to also explain this new design tools that he was creating at Foster & Partners that were able to sort of explore these design potentials of this project, as well as sort of automate some of these tasks of like updating drawings and so forth, was really the answer I was looking for in terms of my own practice. And so I thought, I have to go work for this guy. And so it was at that point, so I made contact with Foster & Partners, and I was fortunate enough that I was able to then move from Bear Happold to Foster & Partners and join Hugh Whitehead and his team in the research and development part of Foster & Partners. You can see here actually on the animation, the parametric model and the creation of these automatic floor plates. So this was like the state of the art at the time in architectural digital technology. So this was the first project I worked on, which was a second stage competition for this large 1.5 km long canopy. And so I adopted these tools that Hugh was developing with Francis H. And you can see here like the parametric model and how I was then, placing these parametric sections, which was then creating these top and bottom surfaces for this giant roof. But the problem was like, once you sort of broke it down to the actual elements that we wanted to create, there was just ends up being hundreds of thousands of elements. And the problem was that parametric system didn't scale. And so how are we going to scale up this parametric system? We need to sort of invent some new tools here. Again, inventing more digital tools for this project. And this is where I found computer programming, i.e. scripting, which enabled me to sort of create the huge amounts of elements that were necessary for this. So this was part of the stage, I would say, in architectural research where we were developing computational design software for architecture. And a big part of this was the Smart Geometry community. This was one of the early conferences, and you can see the focus of the conference is really on the computer and working with digital software. Robert Aish was a central figure at that time. Robert adopted a lot of the ideas, not only from practice from people like Hugh Whitehead, but also from a legacy of computational thinkers such as Christopher Alexander, who had imagined design as this associative system using these formal graph methods. And so Robert basically turned these ideas into a software. So using visual programming, through connecting these design concepts, one can actually come up with architecture. Therefore, trying to enable some of these ideas that Ivan Sutherland had introduced with Sketchpad, that CAD is not a better way to draw, but a deeper way to think. So Robert likes to think that we're entering into this design computation era, or maybe this is wishful thinking, that we're entering into the design computation era, where the designer is no longer directly modeling the building. Instead, he's developing an algorithm whose execution then generates the building. So this is the software that we were working with at the time, along with other softwares as well. But generative components, where there's like this algorithm, which is expressed as a graph, which then can produce both the geometry of the building as well as a variety of different building data. And so there was these two different approaches that we were using, this associative modeling as well as this computer programming and scripting, and generative components actually had both. And so what we were finding in these projects is that the parametric model not only was able to like be adjustable and all this stuff and create really cool forms, but it enabled this multiple representations of data. And through these multiple representations of data, and what do I mean by that? It's like, it's not just like the architectural drawing, but we could also, you know, include things like about cost, or we could include things about structural performance, or we could include things about environmental performance. And so we were able to connect different disciplines through this data that we were developing. So with this data, we began to then experiment also with digital fabrication. So in the traditional building process, we sort of go from, you know, the drawing on the computer to the production of physical drawings, which are then given to the craftsman who then builds the building. With digital fabrication, we can go directly from the computer to create these digital instructions, which will then create the building. So this is like kind of a cool idea for, especially for those of us working with digital technology and architecture. So we were very quick to adopt this technology. So we had the first 3D printer in a UK architecture office, was one of the first projects I worked on. We were looking at this like complex form found geometries, and I was able to just instantly 3D print these options, which was amazing. And so we were able to produce, you know, hundreds of different iterations, not hundreds daily, but certainly multiple iterations daily. And this became a really key part of particularly this project in terms of its development. As Hugh Whitehead said, the use of rapid prototyping closes the loop in a digital design process, and its recognition that key design decisions are still made from the study of physical models. And this building, here we go, this is the built project here. This is the Constructive Center in Kazakhstan. So what we found sort of from 2005 or whatever, when we got the first 3D printer, 12 years later, the Foster and Partners print shop is producing 12,000 models a year. Huge number of 3D prints. So massively successful at that particular architecture firm. Why is 3D printing so successful? Architects were already working in 3D. So they already have the data. So it doesn't require more work to get the data. Okay, maybe a bit more work. It's faster than hand building. And the cost, even though it costs a lot to 3D print, it costs more to pay an architectural assistant to build that model by hand. And also the limitations of construction disappear, which arguably could be a good or a bad thing. So in smart geometry, we also noticed this shift from software development to fabrication, right? So the first, 6 years of smart geometry are really focused on developing these parametric tools, computational tools for architecture, which didn't exist really for architects at the time. There was, tools for engineers and mechanical design, this kind of stuff, but not really for architecture. So the first 6 years were really developing these tools. Once the tools had been developed, it was kind of like, what can we do with them? And digital fabrication became a key part of that. So this is the workshop, smart geometry workshops in Barcelona, Spain, where a lot of this research happened. And I worked on a project there called Parametric Acoustic Surfaces, where we used digital fabrication, laser cutters, CNC machines, et cetera, to create this performance-driven acoustic architecture. But what I want to talk about is this project here, which was done by Tobias Bontwich and Ralph Berchi, particularly from the DFAB group run by Gramazia Kohler at ETH in Zurich. And they ran this workshop called Explicit Bricks, where they brought a robot to the workshop. And through this programming of, I guess it was this subtractive geometric processes and using this hot wire cutter, they were able to create these bespoke formed bricks, which could then be stacked in these very interesting ways. And so this really was very revolutionary to us as architects, especially coming from 3D printing, which in 3D printing, we weren't imagining was scaling very well to architecture, but we were thinking, wow, this is something that could scale to actually create real buildings. And so again, similarly to before, we have the algorithm, which can create this digital model, but it can also directly send the fabrication instructions to the robot. And Grammatsia Kohler had achieved success using this approach at the time. And they really, I think, should be credited with like this initial research into robots in architecture, investigating the potentials of this technology for application in architecture.
Traditionally, the promise of industrial robots has been that they would replace the human workforce. But these projects, led by the Swiss Federal Institute of Technology in Zurich, demonstrate a different result. Architects are free to create designs and patterns of a precision that simply could not be achieved by hand.
The industry is very interested, but you have to show them that they will have the possibility to address the market with new products that didn't exist, and that they wouldn't have if they wouldn't invest in innovation. This is the point, the whole point. And I think every part of the construction industry could engage in such a process. Now we started with brick industry. What will happen if all buildings will be done by robots to the labor in construction industry? And we had a lot of success because of our products, prototypes we are doing right now, to show to people that have this question that it's not about the substitution of labor, it's about new products. So we are not doing the same thing just with robots. There are a lot of works, of jobs, of things that are very, very difficult for robots to do, and we will never automate. A human is much more efficient with his intelligence and so on. And there are other things you can do with robots. You can do very well with robots, with machines, and those processes generate new products.
The construction industry is very open to these changes because they see that from the architect side of view that the demand for customization is constantly growing. Yet their possibility to react to this is currently very low because with the standard techniques there's a lot of development always to be done. Now with flexible manufacturing and digital fabrication, there's the possibility to standardize new products which are in fact mass customizable. You could imagine that products are no longer conceived just as fixed products which are then repetitively used, but that they are more complex, they have more capabilities and functionalities integrated into them, which are then custom produced by possibly small manufacturers, which can integrate all this information into a building part or an architecture. We expect that the robot can be used right now for the construction industry. I mean, we were lucky to already build a facade with the robot, which was actually 4 months after the first brick was really laid by this robot. The first architectural product was already produced in collaboration with an industry partner, and our industry partner Keller Brickworks from Switzerland is interested in actually bringing out the product which actually uses this technology. The ultimate goal for us is to enlarge the possibilities for architecture and to create direct links between the physical becoming of architecture and the information side of architecture, which developed rapidly in the 1990s.
This gives new possibilities for new designs, for new architectures.
So what we can see from this wonderful project, one of the early projects from Grammatsia Kohler, and what they explain is that for them, robots were not about the substitution of labor. They were in fact about these new processes, new construction processes and design processes then would that result then in new products and this mass customization of architecture, enabling architecture to be customized for clients for different situations. And also key to this is this linking of digital information to physical making. Another point that I want to bring up right now is this rise in building performance and performance-driven design in architecture as well. So I wrote this book I guess it came out in 2017 or 2018 called Computing the Environment. And my wife and I wrote this. We looked at and interviewed people that we knew that worked at a lot of major design firms across the world, architects, engineers, etc. And the conclusion that we came to is that architects are really moving beyond parametric design. And they're moving into this idea of building performance. And one of the things that's enabling this, certainly isn't solely, is this idea of software development using these relatively easy to use visual programming tools, particularly Grasshopper. And what's amazing about the Grasshopper platform is that it's easy to create your own tools within that. So they give instructions about how to create your own plugins to this environment. And so what's happening is we're getting this whole ecosystem of new design tools that are able to plug in to Grasshopper, which plugs into Rhino, which is a CAD software. And so we're getting all of these new softwares that can simulate performance in different ways: energy performance, lighting performance, acoustic performance, et cetera, et cetera. So Phil Bernstein, who was one of the leaders at Autodesk for many years, writes that where the architectural design process in the pre-digital age was one of careful contemplation, limited calculation, experienced intuition, and ultimately judgment, today's designer can rely on an array of analytical, simulative, and visualization tools that enhance understanding of an emergent design and predict its ultimate performance. And so the point I'm making here is that we're seeing this radical technological shift in architecture, I think, because of design technology. Number one, through computation. Number two, through digital fabrication. And number three, for this in consideration of building performance. So why are we doing this? Is this for money? Given the salaries of architects that I know, I would say not. Are we doing this for the thrill of invention or for the sake of technology, to push the envelope and take technology as far as it wants to go? And while robots are thrilling, I would argue no. Because it seems, given current evidence, that the quest to maximize profit and unhindered technological development has led us here. Edward Bertinsky, the photographer, in his show recently at the AGO, paints a portrait of the world as it is, a world that humans have made. Titled The Anthropocene, humans now affect the earth and its processes more than all other natural forces combined. And while Bertinsky's images have incredible beauty, it does not necessarily paint a picture of a world we want to live in. And so we need to change, and maybe robots can help. So let us return to robots for a minute. Tesla Motors has been recently criticized that they have over-roboticized. There's need to reintroduce humans. And while robots can be programmed to do repetitive tasks and tasks requiring great strength, somehow they fall down when it comes to tasks requiring decision-making and fine motor skills. Getting a robot to clear tables in a busy restaurant would be nearly impossible, and even opening doors and using power tools is beyond the most advanced robots. Dan Hill warns us that we should not unthinkingly deploy robotics in place of human labor just because we can. Equally, we should not continue to use people as robots. We need to start sketching out positive relationships between people and robot, assessing who does what. Dan Hill proposes a model of shepherd-sheepdog, and I think this model has the potential for particular application in construction robotics. In this framework, the human is the shepherd to the robot's sheepdog. So all three of these projects lie at the intersection between these ideas I've been talking about, between algorithmic design, and robotic fabrication and building performance. So the first project, Sustainable Sonic Environments, is a project that I did with a bunch of research assistants. It started out as a series of experiments we did collaborating with Element 5, creating some acoustic diffuser panels out of cross-laminated timber products, seeing how these types of performance could be embedded within those materials. And here we were looking at the acoustics of meeting rooms and looking at this particular phenomenon of flutter echoes. You can see on the left-hand side, this sort of distinct reflections that can form in between parallel walls, whereas on the right has a more diffuse sound field, which has less of these sort of like distinct flutter echoes. And so we came up with this concept of this wall that would have this sort of continuous surface, which would then become a little bit more modulated in the middle. The algorithm was essentially this central point, this linking point for ideas about geometry, simulation, and fabrication together. And so algorithmic design, like mentioned by Gramazia Kohler, these new processes lead to new products and enable mass customization. And this is something that has been adopted by other industries like Nike. So this is a pair of sneakers I designed just the other day using their online system. And this is something that is certainly, or could certainly be used in architecture as demonstrated by Gramazia Kohler. However, programming robots has been historically difficult and challenging. And this is justified in the case of the car assembly line, as tens of thousands of cars are produced for each one of these programs that you have to program the robot for. However, when you produce a building or a building experiment, there's only one of them. And so how do you program the robot? Like, what's going on? And I would say this has something to do with like this growing knowledge of computation in architecture, but also this increasing ease of programming robots because of things like the KUKA PRC plugin for Grasshopper. So we can see an algorithm here, which is used to stack bricks. And we can see here that there's a section of the algorithm that essentially creates our robot instructions. And this is one of these key things that's going to enable architects and designers to be able to create more of these bespoke robot programs. So here's our 3D model. This is a picture of our robot, or a video of our robot doing the milling of this wall. A little picture of the lab too. It's a finished milled piece, and then this is myself testing the acoustic parameters of the room. This is my my children here. Actually, they're testing the surface as well, inspecting my work. Perhaps they're a little bit less noticing of the acoustic effects, but certainly appreciative of the geometry of the surface. So we've seen that this surface has measured acoustic benefits, but it also provides a visual impression and invites the room occupant to rediscover the wall surface as something to touch, to feel, and to engage with. It reimagines the ubiquitous plasterboard as a customizable surface that can improve the acoustic and visual comfort of the inhabitant. The second project here is Spatial Timber, where we look to understand the rules that go with a reciprocal frame project and then apply this to a more flexible three-dimensional surface. And so for this project, not only do we have to program the robot and all of the moves of the robot, but part of robotic fabrication is also the creation of these customized end effectors. And so we can see here a customized gripper that we made that fits onto the robot, as well as this customized saw table, which is then able to cut these bits of structure to the right precise dimensions that we need. And so this is, I guess, not only cut them, but it's going to place it as well here. And so this is one of the parts of robotic fabrication that we have to address as well. So it's not only just the creation of the design and the creation of the algorithm and the creation of the instructions, which are then sent to the robot, but there's also the design of the whole fabrication system, the creation of the end effectors for the robot, which in a sense can be seen as like this extra amount of work, but also this is illustrative of this ultimate flexibility of the industrial robot. So you're able to put like pretty much any end effector onto the end of this robot, and which enables it to do like almost an infinite amount of things. And so you can see here the robot is placing this piece of the reciprocal frame precisely into the correct spot. And so here's the algorithm, which includes not only design and the fabrication, but also the structural simulation. This is the Grasshopper script here. And then there's this design of the fabrication process. So the placement of all these pick points and lifting points and cutting points and placing points, and an image of our final experiment here. So the third project and last project I'm going to talk about is the gradient acoustic surfaces, where we're looking at this robotically fabricated wall tectonic. We were experimenting with stacking techniques in robots and wondering how we could use these for acoustic performance. And so when an acoustic wave hits a architectural surface, one of three things can happen. It can either be reflected in a specular manner, or it can be diffused, scattered into many directions, or that sound energy can be absorbed. And so what we sought to do was essentially create a series of strategies using these blocks that would create all three of these different acoustic performances. So here we see reflecting surfaces, we've got scattering surfaces, absorbing surfaces, and we combine these into one single surface that we would be able to design. Again, here's the algorithm, which sort of contains all of the different design, simulation, and fabrication. This is the dual gripper end effector, which we designed for this project. Then we use this computer-controlled saw. Again, the design of the fabrication process. And here's a video, that's sort of time-lapse video, obviously, of showing the robot constructing this. And you know, I talked about Dan Hill and this sort of shepherd sheepdog. This is really what we're doing here, as well as sort of working with the robot to help it build the wall. This happened over a couple of days, as you can see by the lighting in the outside background. We were running the robot on a much slower speed, this being the first time we're running it. If this was actually done in some sort of commercial application, you could speed up these processes like a lot. So I research and practice within the computational design community in architecture. Within our conferences, journals, and events over the last 10 years, we've seen an incredible shift of attention towards the potentials of robotic fabrication. Architects are captivated by robots. As this recent book blatantly states, even when they do nothing, robots are evocative. I believe that this newfound interest in robots by architects lies in more interesting narratives. Narratives that relate to the changing nature of practice, relates to architects' role in practice, and I hope I have illustrated a few examples of that here today. So why are architects interested in robots? Is it because they make beautiful things? Perhaps, and perhaps this has something to do with it, but I believe that it goes beyond form. And I think it really has something more to do, or not everything. I'm not proposing that this is an answer, but this is part of the answer. Is that the design and fabrication through robotics enables this like creation of building tectonics that are responsive, not only to design intention, but also to performance and to materiality and assembly processes. So for architects, robots are not about productivity, it's not about profit, and it's not about dirty, dull, or dangerous. So if computation can help us design a better world, maybe robots can help us build a better world. Thank you very much.
Excellent. Thank you so much for the presentation, Dr. Peters. So we'll now do the Q&A session. We're approaching time, but I'm going to let it run a little bit longer so that we can have time to get a few questions in. Just a reminder that if you have a question for our presenter, please use the Q&A box at the bottom of the Zoom window, and I'll try to get through as many questions as possible. Just while folks, to give folks a minute or two to get into pop in their questions. So based on where the research is going in your own experience, where do you see all this going in the next 5 or 10 years?
All of this as in all of design technology, or all of
all
robots?
all of the life, the universe, and everything, or robotics in the use in design and architecture and construction.
Yeah, that's a really good question, and I wish I knew the answer to it. But what I certainly tell my students, in terms of design technology, which is what I teach at the university, is that, like, in the 20 years I've been practicing, I have seen an incredible shift in what we do. If we think about like those first like parametric models that Hugh Whitehead was doing for Swiss Re, and we think about what we could do now, the software we used then, we don't use anymore. And so we have to be flexible because these new technologies are coming all the time. And so we have to adapt to change. But at the same time, I think that some things are slow to change. And so with industrial robots have been around for ages and ages. And in fact, even in architecture, the Gramazio-Collo experiments started in 2006 approximately. 2008, they became very much more widely known. Nowadays, there are robots in certainly all of the leading schools of architecture across the world, and many schools of architecture. And so we're seeing like this massive uptake, but it's going to take a while before it like bleeds into practice, I think, in terms of impacting these. There's a certain inertia in the construction industry, and in terms of clients. Changing architectural design processes, I think we're only changing one group of people, but as soon as we start changing like an industry as a whole, we need to sort of, it's just going to take a little bit longer.
For a business, construction business, or I guess a architecture design firm, either or, that wants to start getting into the use of robots for design and construction, the way you've sort of laid it out today to build those new products and those sorts of things. What are some of the interesting places to start or keys to success that you might suggest they want to look at as they begin exploring it?
Well, this is a good question. And I think, like looking at the case study of perhaps Foster and Partners, who's like one of the world's leading architecture practices, and certainly leading in terms of the adoption of technology. They didn't have robots when I was there. And I know many of the people who work at that research group, and I know that they certainly looked at robots. But actually they couldn't make a case for it to bring it into the group as a design tool. Perhaps they've got a smaller robot to do some smaller exercises, but it certainly wasn't something that they thought was absolutely critical, whereas the 3D printer made a massive change. So I think that the adoption of these industrial robots into architectural practice really happens at this intersection of construction and design. I think that's where it will really have the most impact, is sort of in this where designers meet constructors, building these really interesting projects that have something to do with form and performance and are challenged to be built in any other way. I think that's where we're first going to see inroads being made into this adoption of robotic technology. So
it sounds like a lot of this is sort of sitting at extremely early stage, and there's probably some work or adaptation and research that needs to be done to move it really into practice. Are there particular aspects of the technology associated with robotics and their use in design and architecture at that intersection that you think would be really well suited to business academic research project that might help it move from sort of the lab into practice?
Well, you know, I think that's a good question. It's one of these problems, I think, where on one level it's like very frustrating because it seems like all the answers are already there. The pieces are all on the floor. The puzzle pieces are all on the floor. We just have to arrange them. And so I think it's going to take a group with some confidence and the right projects to pick up these pieces and show that it can be done in an economic way that makes sense, that creates a new product using these new processes. So I think that's really the thing, because, and I think it could happen quite quickly once the right people come together, because like I said, the pieces are there already. So the design technology is there. There's certainly like we're training people at University of Toronto that have the skills that can be then, you know, take this forward. So there's certainly designers. I would say we need to have some educated clients that sort of are interested in this, and we need to have some constructors that are interested in the investing in this technology. So while I said, you know, these robots are inexpensive, I would say they're relatively inexpensive. So they still cost a couple $100,000 to get this, to get one set up and so forth, and you need to have the space to do it. But I think in terms of like the benefits of that, they're not very expensive at all.
That's extremely helpful. And that pretty much brings us to time. So first of all, I'd like to thank Dr. Peters for his presentation. I know I found it extremely interesting, and I'm sure others did too. I'd also like to thank Kenny, Nicole, Mary, and the rest of the team at the CCA who have been so instrumental in pulling this session and this series together. Without them, this really would not have been possible. I'd also like to thank all of you for coming out today. I know your time is scarce and precious, and really appreciate you fitting this into your busy schedule. On that note, we're really focused on making sure these are as valuable for you as possible. To that end, we've created a short evaluation form that we would really appreciate if you would fill out. I pasted a link in the chat window. In addition, it should open in your browser if you haven't already closed the Zoom tab. It should take about 1 minute to fill out, and your honest feedback is really essential and important to us as we continue to move this forward. Thanks again, and I hope everyone has a wonderful rest of the week.